Now this operation of finding a threshold is called really is a very, very important operation called thresholding. Okay, image thresholding. Now finding a t, right, seems to be an important thing. For example, if I give you an image, and suppose it's actually a grayscale image, and suppose I ask you to convert it into really into let's say a binary image. Okay, then it actually means that you need to find some kind of a threshold. Okay, and then you ought to be able to examine every little intensity here, and then you have to be able to say whether that intensity is greater than t. If it is greater than t, you make it 1. If not, then you actually make it 0. So if it is less than or equal to t, you make it 0, right? And that way, okay, you start entering zeros and ones and so on, right? And then you get what is called a binary image. Right? And there are of course many instances when you want to convert something that is grayscale into a binary. Now, binary is one form. You could also ask for not just binary. You could ask for what is called a multi-level image. In which case you might say that right, break it up into 4 regions or whatever, right, 4 levels instead of just get us right 2 levels. You might want to break it out into 4 levels and so on. But suppose we come back to the more simpler version, which is really a binarization. It is kind of a 2-class problem, right? I mean, you want to be able to tell whether this pixel belongs to class 1 or class 2. So class 1 is like all zeros, and class 2 is probably all ones, right? So you want to kind of put them into either a basket like this or the other basket. Now, in order to be able to kind of do this, you have to be able to find t, right? And then finding t seems to be the key, because if you choose a t that is too high, then maybe right, you might actually make things, then you might actually end up doing things wrongly. If you take t too small, again you might end up doing things wrongly. Therefore, there ought to be some notion of what should be an optimal value for t. Now, one of the things, right, that actually helps you find t is really what is called a image histogram. Okay, image histogram. What is a histogram? A histogram is something that actually converts your 2D image into a 1D plot. So what is this 1D plot now? So histogram is really a 1D plot where along the x-axis you have the intensity levels, and then along the y-axis you have the frequency of occurrence of these intensities. So it's like saying that the x-axis has values like 0, 1, 2, 3 all the way up to, let's say, 255 if you had 256 levels and all. And then, right, your image, okay, suppose I count suppose in this grayscale image I count the number of times 0 occurs. Maybe it occurs here, maybe it occurs there, I count how many times it occurs. Suppose that occurs 4 times, then f of 0 is 4, right? Then I would have this, let's say f of 1 is some 7, let's say f of 2 is something else, f of this is something else, maybe, right, maybe some intensities just don't occur at all. It may be, right, 3, you don't have 3 occurring at all here, maybe 4 occurs, something else occurs, and maybe, right, 255 occurs, maybe, right, 2 times and so on. So this plot is really called the histogram, right? So it's a 1D plot, okay, and because of the fact that you've converted information coming from a 2D and you have squeezed it down to 1D plot, then it actually means that you're going to lose information. You lost information because you cannot go back from here to there. And even if I give you the histogram, right, we haven't stored information about where these intensities came from. All that we said was how many of them were there, right? So we don't have information to kind of go back. So I don't know where to put these zeros back there. So only in special cases you might be able to go back and reconstruct, but in most cases you cannot. So the spatial information is gone, but that is okay, right? We are all right with that, because, right, even having this 1D plot helps us a lot. Okay. Now, how does this 1D plot really help us, this histogram, in order to achieve a thresholding operation, right? What this boils down to is this: suppose you're very lucky. Let's say you're very lucky, and your right, I mean, image simply had, let's say kind of 2 values. So let me say that this is something like 40, and let's say this is something like 200, and this is I after you plotted the histogram. This is what you observed. Now your job is very easy, right? I mean, if you want to binarize this image, you simply say put a kind of a threshold, right? Anywhere in between these 2 values, wherever you want, and then you say, right, all the intensities intensities in the image that have a value less than this t that you have chosen, go to class 1, and all the ones that are above, okay, will go to class 2. Right? This is very simple. This will seldom happen. Okay, this kind of a thing will seldom happen. So what you will normally encounter, right, is something like this. You will actually encounter a histogram. Suppose I try to draw a continuous curve, right? You might get something like that, or kind of right something like this, or something like that, right, and so on. Now, right, you need not have just two modes, and sometimes, right, I mean, you might also get right, multimodal histogram and so on. Of course, all of these, right, you have to kind of remember that I should be is typically a discrete value. Therefore, even though I've drawn a continuous curve, it really means that right, these values exist only at 0, 1, and then 2, and so on. So at 1, at 2, it has a value. This 1, it has a value. This I just drew a continuous curve just for understanding sake, but really, right, in an image you have only a discrete set of intensities, and for which, right, you'll have the frequency of occurrence for each of those intensity values. Now the point is right, if you have something like this, and now here, right, you want to ask us to, if you wanted to do something like a binarization, or really a thresholding. So binarization, let's say, which is like dividing into kind of two classes. So you want to know, should I put my threshold here? Should I put my threshold here? Should I put my threshold there? Where should I put my threshold? And so you need some kind of a sense to, right, pick up the T. Now there is a host of these kind of techniques, okay, that can actually do this job. Okay, what are called the thresholding methods. And you can fundamentally classify them into right, two of these categories. One is called reconstruction based, which I will skip, because reconstruction is something similar to a PCA, right, that we did, in the sense that, right, I mean, reconstruction is like, I mean, if you had this, for example, then one of the ways to do it would be to approximate this histogram that you have with actually a sum of Gaussians. So you would have to find out, what should be the sigma of each Gaussian, what should be the mean of each Gaussian, what should be the weight of the Gaussian, and so on. So basically, your unknowns kind of turn out to be that, and the whole idea is that how best can you fit a sum of these Gaussians to this histogram plot, right? That's why we call it reconstruction based, because the error, right, that you get, you want that error to be as small as possible between the original histogram that you have with you and then a Gaussian fit, right, which you're kind of, right, trying to do. If it is bimodal, then you have two of these Gaussians. If it is multimodal, then you have, let's say, if you have n modes, if you know that this histogram, you want to model it with n modes, then you will have like n of these Gaussians, each one with its own mean value and its right sigma and so on. So this is called reconstruction based, somewhat along the lines that we did for PC and all, right, where you want to reduce the reconstruction error, right? There also when we said we'll pick the significant eigenvectors and expand, then the whole idea was, how do I do so that my mean square error is as small as possible. So here it's a reconstruction error. So you have this histogram, you have the Gaussians, some of the Gaussians, and you're trying to find out how best, right, can this least squares fit be done. The other way to do it is really a discriminant based approach, which is what I will talk about, okay, in this course, which is called a discriminant based. Okay, what this means is that, so it talks about, it's not the same as reconstruction. So in order to, right, give you an example by what we mean by a discriminant based approach, right, I'll just go back to the face example that we talked about earlier. Suppose I gave you a bunch of faces, right? Suppose I gave you a basket, right, full of face images. Now this consists of, let's say, 4 individuals. Okay, we have face images of 4 individuals, and let's say, right, I mean, we wanted to see how well to kind of recognize them. So one way to do it is actually go through a PCA, which will be a reconstruction based approach. We will compute eigenvectors, whatever eigenfaces, and then right, we will have the feature vectors for each of these persons, each of these people. The other way to do it is, so which means that we choose a certain basis, right, which are in terms of these orthonormal eigenvectors. The other way to do it is really what is called a discriminant analysis, linear discriminant analysis, in which what you do is you kind of pick pick the basis. That means you pick these vectors, right, such that you maximize interclass variance and minimize interclass variance, and minimize intraclass variance. intraclass variance, or what is called that is a between class. Interclass is like a between class variance if there are two. Intra is like within class, right? So what this means is that, right, you want to choose the basis such that, right, such that you get kind of classes like these. Okay, you're able to separate these classes. You don't really care about how well your reconstruction happens, but you're more concerned, or you're more focused on the fact that the separation between these classes should be high enough. But then the intra-class, that means within each class, the variance should be small. It amounts to saying that if I have a person, right, this is, let's say, person number 2, this is let's say phase 2, phases of the person 2. What it means is that even if I have images of this guy that come under different illumination, different expressions, different poses, I want to call all of them as this guy, right? I don't want to say that, I don't want to say that if the expression changes, then he is someone else. So the within class variance I want it to be small, because that is when I want to ignore these sort of intrinsic variations, right? I want to ignore the intrinsic variations, and therefore I want to reduce or make the within class variance as small as possible. But then the interclass, interclass is what helps me separate them, and therefore the interclass variance should be as large as possible. Now the thresholding, right, that goes by this kind of a discriminant based approach is one such approach that uses a discriminant analysis. A discriminant based approach is what is called Otsu. And the reconstruction based, one of the kind of popular methods is Chow Kaneko. Now Otsu, right, it goes after somebody's name, right, whose name is Otsu, and I want to kind of talk about how this kind of a thresholding scheme works. Okay, in more detail, right? So let us go and explain what is Otsu thresholding. Otsu thresholding. Now, the way this works is, right, so it's like this. I mean, I have a histogram with me, right? Somebody gave me an image, and I want to right, this is a grayscale image, but I want to kind of do a binarization, and I want to convert these intensities into either 0 or 1 depending upon some criterion. Now it could have some kind of a histogram, right? And suppose I choose some value. So let's say I choose a small t, right? The point is, what should be the optimal value of t, and what is my optimality? This one. What is the optimality criterion? Okay, that I'm going to use in order to find my t star. Okay, so how do I find a t star which is optimal? So the way this Otsu goes about, right, is like this. Now suppose we select a threshold t, right, arbitrarily. Suppose we start with some t, okay, and then we say how to kind of get to t star, which is the optimal t between, let's say, intensities between 0 and L. Okay, so here is our intensity 0. Let's say the maximum is L. Could be typically 255, but let's say, right, for the sake of the generality, we'll say it's L. Let f of I represent the number of times the intensity I, occurs in the image. Okay, similar to this plot, right, that we have shown. Let n1 be the number of pixels in let's say number of pixels in class 1, and let n2 be the number of pixels in class 2. Okay. Now, if for a threshold t, right, if you choose a threshold t, right, let us kind of look at the mean. Let us examine the mean and variance, let us examine the mean and variance of both the classes, of both classes. All right. So what does that mean? So suppose we say that mu1, right, is really the mean of the first class. This will be a function of small t, right, this a threshold, okay, which we are choosing. So mu1 of t will be summation I equal to, because this just involves all those intensities that are less than or equal to t. So we will say 0 to t, then I into f of I, where I is the intensity, f of I is the frequency of occurrence of that number, divided by n1, because class 1 has only n1. n1 is number of pixels in class 1, right? And therefore the mean of this class is IFI by n1. Now the variance of this class, let's indicate it as sigma 1 square, and that's also a function of t. That will be I is equal to 0 to t, again I minus mu1 of t. Now, right, I may not repeat this mu1 of t every time. When I write mu1, I think we'll assume that it's a function of t, square f of I by n1 again. Now similarly, right, for the second class we have mu2 of t given by summation I is equal to, now this goes from t plus 1, right, because this is the class that involves intensities greater than t. So t plus 1 to L I into f of I, now obviously divided by n2, right, n2 number of these pixels in class 2, and similarly we have sigma 2 square of t that we can write as summation I is equal to t plus 1 to L I minus mu 2 of t the whole square into f of I by n2, right. Now let us define the within class variance, the within class, or what is called the intraclass variance, within class variance as sigma square w, okay, w stands for within class, sigma square w of t is equal to summation sigma j square of t into nj by n, j equals 1 to 2, okay, where so where this denotes probability of the two classes nj by n, okay, that is your sigma square of t, say sigma square w of t. Now what about this total mean and variance of the entire image, total mean and variance, right? If you look at the total mean and variance, that will not be a function of small t, obviously, right? That is not going to be a function of small t. So mu t will be simply summation, right? So when you look at mu t, right, you've got I is equal to all the way from 0 to L I times f of I by n, okay, and I have not made this a function of t, small t, because it is not. Similarly, the variance is also not a function of t, so we will not put bracket of t. We simply say this is equal to I equal to 0 to L, then I minus mu t whole square f of I by n, okay. This is the overall mean, what is called a total mean and variance. Now note that, right, both of these are these are constants, right? Mu t is a constant, sigma t is a constant, these two, sigma square t is a constant, these two do not depend on small t. Let us also look at the between class variance, because what we did was within class. Now let us examine the between class variance. So between class, let us indicate it as sigma square b of t, right. So sigma square b of t is summation j is equal to 1 to 2 mu j minus mu t the whole square into nj by n, where of course, okay, ideally I should be putting mu j of t here, because mu1 and mu2 depend on t. Mu t, of course, this is independent of t, okay. This ideally I should put mu j of t, but then from now on I'll drop the t, okay, but we'll assume we know for a fact that mu 1 and mu 2 depend on small t. Now I leave it to you as an exercise to show that, right, this can also be written in the form, see, if you kind of look at this, right, this is looking like mu j minus mu t whole square. I know I want to leave it to you as an exercise to show that sigma square b of t can also be equivalently shown as some constant times mu 1 of t minus mu 2 of t whole square. Okay, because in a way, right, I mean, you might be able to interpret this in a more easier way than this, but then these two are exactly equivalent. Okay, so when we say the between class variance, this is what we mean. Okay, either you can write it in this form, or you can equivalently show that where a is a constant. You can show that. I'm not going to tell you what is a. You should find it out. Okay. Now, what we want to do is we want to show that it can be shown that sigma square t, which is independent of t, is in fact sigma square w of t plus sigma square b of t. Okay, which actually which actually has kind of a nice interpretation. What it actually means is that because sigma square t is actually a constant, right? We know that this is independent of t. So if you try to minimize within class variance, this will automatically maximize sigma square b, because sigma square t should remain a constant. This is a constant. Right? Because this is a constant, and minimizing the within class variance is equal to maximizing the the interclass variance or between class variance. And similarly, maximizing between class variance, or if you try to maximize between class variance, then it will be equivalent to doing a minimization of the within class variance. So it means that we need to do only one of the two. Either we should minimize this or we should maximize this. Between class, either maximize between class, or you should actually minimize within class variance. So doing one is equivalent to doing the other, because of the fact that sigma square t is a constant. Now we want to go ahead and show this now. How do we show that? So let us start with sigma square t, the expression for sigma square t. So sigma square t is summation I is equal to 0 to L I minus mu t the whole square f of I by n. Right, this is bad. Okay, this is what we had. Now let us split this into two terms. I is equal to 0 to t I minus mu t the whole square into f of I by n plus summation I is equal to t plus 1 to L I minus mu t the whole square f of I by n. Now furthermore, let's just play a small little trick. We'll do it as I is equal to 0 to t. I'll just add and subtract I minus mu 1 plus mu 1. Mu 1 should be strictly a function of t, but I'm not going to explicitly write that. Minus mu t the whole square into f of I by n plus summation I is equal to t plus 1 to L. I'll add and subtract mu 2 here. I minus mu 2 plus mu 2. This again is a function of t, although I'm not writing it explicitly. Minus mu t the whole square into f of I by n. Now if you expand this, this will turn out to be summation. Now we'll instead of looking at both the terms, we'll just look at one. Okay, examine this. Examine the first term. Okay, examine this. So if you examine this, what do you get? You can expand this as summation I minus mu 1 the whole square into f of I by n plus summation 2 times I minus mu 1 into mu 1 minus mu t into f of I by n plus summation, okay, all the way, of course, I equal to 0 to t here, I equal to 0 to t here, I is equal to 0 to t here, obviously mu 1 minus mu t the whole square into f of I by n. Okay. Now this term, we can rearrange it as summation I is equal to 0 to t I minus mu 1 whole square into n1 by n into f of I by n1. Okay, because we have just multiplied and then divided by n1, right? So f of I by n. Now, if you pull out n1 by n, this will be equal to n1 by n summation I minus mu1 whole square into f of I by n1, I equal to 0 to t. Now, this clearly, right, you can actually identify this with, this is sigma 1 square of t, correct? If you kind of go back and check the expression, this is what we had for sigma 1 square of t. Okay. Therefore, this whole thing reduces to n1 by n sigma 1 square of t. So, the first term, right. So, the first term, this reduces to this. Now, let us kind of look at the last term. The last term is mu 1 minus mu t the whole square. So, summation I is equal to 0 to t mu 1 minus mu t the whole square into f of I by n. Okay. Because of the fact that mu 1 and mu t are both independent of I, therefore, this can be written as mu 1 minus mu t the whole square into summation f of I by n, I equal to 0 to t. Okay, this we know is simply I equal to 0 to t. If you count all of f of I, that is simply equal to n1. Therefore, this is n1 by n into mu 1 minus mu t the whole square. Now examine this middle term now, right, which is still remaining, which is I minus, so 2 times I minus mu 1, right, so this term, right. So, out here what we see is mu 1 minus mu t is independent of I, therefore, right, that can be pulled out. So, you will get 2 times mu 1 minus mu t into summation I equals 0 to t mu, and then what do you have here? I minus mu 1, sorry, I minus mu 1 into f of I by n, right. Now, this can be split as summation I into f of I by n, okay, I going from 0 to t minus mu 1, which is of course independent of I, into summation I equal to 0 to t f of I by n. Now, if you see this is I into f of I by n, and right, this we can write as summation I into n1 by n into f of I by n1, which is equal to n1 by n into summation I into f of I by n1. This we know is mu 1 of t. Therefore, this will be equal to n1 by n into mu 1 of t. Okay, this is I equal to 0 to t, of course. Look at this. What have we got here? This summation is simply mu 1 into summation I equal to 0 to t f of I is n1 by n. And therefore, right, these two are exactly equal and they subtract each other. Therefore, this term will go to 0. So, therefore, what this means is that the first term, right, if you look at the first term here, this term not this, the first term is this one. So, this term in fact reduces to n1 by n sigma 1 square of t, which is what you had here, and the second term, which is n1 by n into mu 1 minus plus n1 by n into mu 1 minus mu t the whole square. Similarly, the second term, right, when you do it from I equal to t plus 1 to L, I will leave it to you as an exercise. Please show that this is equal to n2 by n sigma 2 square of t plus n2 by n into mu 2 minus mu t the whole square. And therefore, right, so therefore what happens is, so the sigma square t, right, if you add up, so here, right, so this whole expansion will then be summation j equal to 1 to 2 sigma nj by n into sigma square j of t plus summation j equal to 1 to 2 nj by n mu j minus mu t the whole square, right. So, these two terms come from here, and this we know is nothing but your sigma square b of t, sigma square w of t, and this we know is sigma square b of t, and therefore it follows that sigma square t is equal to sigma square w of t plus sigma square b of t, right? Now the implications are as follows. Given the fact that sigma square t now is equal to sigma square w of t plus sigma square b of t, right? So if you find a t such that it maximizes between class or minimizes within class, we are done.